A brand new model just dropped, and it's not just big, it's the largest open-weight model ever released. Today we're putting Kimi K3 through a full battery of tests. Browser apps, 3D engines, full websites, an FPS shooter, and even a cinematic game. Let's see if the size actually translates into real capability. Kimi K3 is a 2.8 trillion parameter mixture of experts model, by far the largest open-weight model on the market. Only a fraction of those parameters are active per query, which is standard for MOE architecture, but the raw scale alone puts it in a category of its own. The team behind it claims it ranks just behind Claude Fable 5 and GPT 5.6 Sol on their internal benchmarks. Big claims for an open-weight release. It also ships with a 1 million token context window and native vision input, so it can read screenshots, not just text. Pricing is where it gets interesting. $3 per million input tokens and $15 per million output tokens. That's noticeably more expensive than most open-weight models we've seen before. But for reference, GPT 5.6 Sol runs around $30 per million output tokens, and Fable 5 is closer to $50. So if the intelligence really holds up, K3 undercuts the closed-source flagships by a wide margin. Full weights are being released in the coming days, alongside a technical report. For now, we're testing through the web chat and API. Let's start with games. Whether it's a browser-based minigame, a full C++ project, or a 3D printable engine model, every one of these results comes from a script built around the same 4 pillars. First, setting an atmosphere. You have to describe the world before anything else. Is it a late 90s shopping mall, an abandoned subway station, a voxel sandbox? Vague settings produce generic results. Specific sensory details, wet floor tiles, flickering signage, a particular decade's aesthetic, give the model something concrete to render. Second, core mechanics. This is the non-negotiable functional spec. Movement controls, what happens on collision, how combat or scoring works, what the win and lose states look like. The more precisely you define behavior, sprint increases footstep pace, reload visibly ejects the magazine, the more that specific behavior shows up in the output. Third, technical constraints. This is often the most overlooked piece. Specifying deliverable format, a single self-contained HTML file, no external libraries, must run in browser, forces the model to solve problems from first principles instead of leaning on shortcuts. It's also how you test raw capability rather than library-assisted output. Fourth, physical or logical feasibility, which matters especially for anything meant to exist in the real world. A 3D printable design isn't just about looking good. It has to account for support-free geometry, moving parts, and real-world tolerances. This is where a script needs to specify function, not just form. Put those 4 elements together, and you get a script that reads less like a wish and more like a spec sheet, which is exactly the difference between a rough first draft and a genuinely playable result. It's tempting to credit results like these entirely to parameter count. 2.8 trillion parameters sounds impressive on its own, but the structure of the script is doing just as much work as the model underneath it. A frontier-scale model given a vague, one-line prompt will still produce something generic. The same model given a structured script, setting, mechanics, constraints, feasibility, or hero, function, aesthetic, content, format, is what actually produces something worth showing. So next time you see a jaw-dropping AI-generated game or website, remember, it's rarely just the model, it's the script behind it. If you want templates for structuring your own game and website development prompts, they're linked below.